So Newton has this beginnings of an understanding of the science of mechanics, and the first problem to which he's going to apply it is Kepler's recent results about the motion of the planets around the sun, and Newton has a beautiful chain of logic that we can actually follow that allows him to derive the fundamental physical principle that we suggested might be underlying Kepler's answer. Newton's mechanical understanding tells him that, as we saw, if an object of mass m is moving around in a circle of radius r with uniform speed v, which is a simplified version of the elliptical motion that Kepler actually studied, Newton was doing the general case. We know that moving around in a circle involves a centripetal acceleration towards the center of the circle. So if you see anywhere in the universe an object that is governed by Newton's laws, like everything is, moving around in a circle of radius r with speed v, then there is a force acting on that object and attracting it towards the center of the circle in which it is moving, and the magnitude of that force is the centripetal acceleration that we computed, v squared over r, times the mass of the object, because F equals ma. If you know the acceleration, you can deduce the force. Now, Newton follows, the moon orbits the Earth. The moon is actually moving in a circle about the Earth. So we know that there is a force acting on the moon, which we can compute if we know the radius of the moon's orbit. And then, because you know how long it takes to go around, you know its velocity. If you knew the mass of the moon, you could compute the force that the Earth applies to the moon in order to keep it moving in a circle. Why do I think the Earth applies it? Well, because it's directed towards the Earth. That's a natural guess. But there's another ingredient here. We know that the Earth attracts everything. Little rubber balls fall onto the Earth because there's this attractive force we call gravity. Apples fall on people's heads, apocryphally. Could it be that the force that keeps the moon in orbit around the Earth is the same as the one that makes tennis balls fall? Well, Newton says, probably. Let's take this seriously. Extrapolating that, let's look at another system. We know Kepler found that the planets orbit the sun in, well, almost perfectly circular orbits at almost uniform speed. Again, that means that acting on each planet is a force directed towards the center of the orbit, in other words, the sun, and we can compute that force. So it makes sense to guess that the sun will be applying this force, and the sun therefore applies a force on all the planets. Then by Newton's third law it would follow that since the sun must be applying force to all the planets, among them the Earth also applies an equal and opposite force to the sun. In other words, if the sun applies a force to the Earth directed towards the sun, it follows that the Earth applies a force to the sun directed back towards the Earth. And now we have lots of cases where the Earth is applying a force to things directed towards the center of the Earth. Perhaps that force too is the same force that makes the moon orbit the Earth and apples fall on people's heads. It all hangs together in a beautiful framework, and we can do the math. So let's start with the idea of something orbiting the sun. So we'll have a planet. We'll call its mass MP. P stands for planet, any planet. And if it orbits the sun at radius r with speed v, then Newton's understanding of mechanics tells us that the force the sun applies to that particular planet is the mass of the planet times v squared over r for that planet. Now, 2 clips ago when we studied Kepler's laws, we found that in fact for any planet that orbits the sun, there is a relation between v and r that is independent of which planet you are considering. For all of the planets, the square of their speed, v squared, is 4 pi squared divided by this interesting constant that I called k for Kepler, times the radius of the planet's orbit. So I can put this expression into that, and I can find F is equal to the mass of the planet times the square of its velocity, 4 pi squared over kr, divided by the radius of its orbit, or rearranging things a moment for a bit, 4 pi squared divided by k times the mass of the planet divided by r squared. Why is this a way to write it? Because the mass of the planet is a property of the planet. R is something that changes between different planets. 4 pi squared over k is the same for all planets. So let's see what we do with this. Well, remember, the idea was that it's all going to hang together, it's all going to be the same force. The sun applies a force given by this expression we found to each planet, and to all the planets it applies the same, the force given by the same constant k. By Newton's third law, each planet applies a force of that magnitude, this precise magnitude, to the sun. Now, universality says that the force that the planet applies to the sun, the force that the sun applies to the planet, should follow from some physical principle that doesn't say, well, the sun is one thing and the planet is another. They're both physical objects. And so symmetry between the two objects tells us that if it's proportional to the mass of the planet, it should be proportional to the mass of the sun. And of course I can do that without any problem. I can say that there is some constant, which I will call g, and if I write that constant such that it's related to k and to the mass of the sun by this relation, then the force expression that I'm writing is equivalent to F is g times the mass of the sun times the mass of the planet divided by r squared. The advantage of this formulation over this one is that here it's clear that there is a symmetry. What the planet does to the sun does to the planet. The force between them is equal in magnitude and opposite in direction, and so there's this symmetric way to write it. But it was clear already that this object here doesn't depend on the planet, so it has to be some property of the sun. The only wild leap here is that the property of the sun it depends on is the same property. The mass and the dependence is the same as the property of the planet upon which it depends, since it determines the force in a symmetric way. And now we can jump to the fact that it's much more universal. Remember, the sun attracts the planets attract the sun. Earth attracts the moon, and the moon pulls on the earth. And in fact, the only way to get a consistent understanding of this is to imagine that the force of gravity is truly universal. Any object applies a force to any other object in the entire universe, and the force is proportional to the mass of the two objects. It's inversely proportional to the square of the distance between them, and there's this universal constant of gravitation that defines what gravitation is and how powerful it is, which very appropriately is given the name Newton's constant. The first measurement we have of Newton's constant is in 1798 by Cavendish, who actually measures the gravitational attraction between two metal balls whose masses he carefully measures separately. So he can actually measure the distance and the masses and find the force and extract a value for g. And g is in the units that are convenient to us, given by this number, 6.67 times 10 to the minus 11 newtons times meter squared per kilogram squared, so that when you multiply it by two masses, kilogram squared, divided by meter squared, you get a force in newtons. So we have this equation, and the way in which it is superior to everything that we have seen so far cannot be overstated. This is a universal statement about anything attracting anything else, and from this follows, for example, Kepler's third law, and of course, by a little more math, all of his other laws describing the motion of the planets, the motion of the moon, and as we shall see, plenty more things. So we found the deep underlying physics that we were looking for, or Newton found it, and we have gotten there.